All right, so this lesson might be a little bit longer in terms of the review video, which I'm sorry about in advance, but this one's super important. So I want to make sure that everyone gets it um, as well as possible. So this lesson 7 and 8 kind of talk about equilibrium in two different forms. So lesson 7 talks about particle equilibrium, which is fairly simple. It's much easier than um, rigid body equilibrium. So that's kind of why they go over it first, is to give you an introduction to the concepts of equilibrium. So the particle aspect of particle equilibrium just says that it's acting on a single point that's infinitely small. So all of the forces will essentially meet up at that point, which makes it a concurrent force system, right? So the equilibrium part of that means that there is no net force or moment on the body. So basically, because we're in statics, equilibrium is going to mean that because the object is not moving, all of the forces and all of the moments must add up to zero in each direction. So in terms of particle equilibrium, the steps are kind of simple and they kind of go like this. So the first step is to evaluate the system. So I put a practice problem right here. So this is the practice problem we're going to go through. So you want to evaluate the system, verify that because it is a particle, all of the forces should be concurrent. And here they are because they meet up at this point right in the middle of point A. So that you know, and then because they're all concurrent, there is no moment happening on the body. So because I'm pulling at everything at one point, there is no reason for this body to want to rotate. It's just going to move up, down, left, or right. Now look at the forces that are acting on the body. So I have three forces. They're all acting in different directions. I have 500 pounds acting straight down, 210 pounds acting up and to the right at a 20-degree angle from the positive x-axis. And then I have some unknown force x right here acting up and to the left at a 35-degree angle from the positive right axis or positive y-axis. So basically I have one unknown, and that's going to kind of how these problems show up from now on, is that you're going to have some unknown in the problem that you have to apply lessons 1 through 6 to solve. So reading the problem, they might give you more information, um, but because of that, you want to redraw the system, right? So if you have a problem that doesn't give you either of the angles in the drawing, they just tell you them in the problem, you want to redraw the picture that they give you under, like, you know how in a worksheet they usually have a little bit like a blurb and then a picture. It'll kind of be like that. So you'll have a blurb, and then if there's multiple things missing, but it gives it to you in the paragraph, redraw it so that you can include those things in the drawings. So once you've done that, find what unknowns they need you to find. Like essentially find what your answer should be or what your answer should describe. And then once you're familiar with that, you're going to end up writing out your equations. And because there is no moment, from these equations, you know that this one's going to go away for particle equilibrium. So essentially what you should have is that some sort of x values add up to equal 0, and some sort of y values add up to equal 0. So kind of what I wanted to do real quick is go through this example problem and write out those equations. So looking at the sum of the forces in the x direction, so that's basically what that means, is sum of the forces in the x direction, and I'm going to call right the positive direction. And I know by definition of equilibrium that those have to equal 0. So then what I'm going to do is I'm going to say, okay, I'm looking at this force first. So I know it's pointing to the right, so it's positive. I know the magnitude as a whole is 210, and then I know it's scaled down by this angle 20. And because this little angle arc here is touching the value that will be the x-axis, so like this is the force that I'm looking for this equation, I know it's going to be cosine of 20 degrees. And again, that's because that arc label thing is touching that side. Now the 500 pounds acts straight down, so there is no magnitude of that force in the x direction, so we can skip that one for this point, for just the x equation. For the x pounds, this one, the one with our unknown, It's pointing in the left direction. I don't know the magnitude, but I know that this side here, oh no, the side up here is the side that's describing my x direction. And that is opposite of this arc angle. And because it's opposite, I know it's sine of 35 degrees. So then what I can do is I can rewrite this equation later to solve for x. And that'll give me the magnitude of that force. So technically I'm done because I have one unknown, which means I only need one equation. But I'm going to show you how to write out the other one just so you know. So the sum of the forces in the y direction is 0 by definition, and I'm calling the up direction positive. So I know right off the bat that 500 pounds is negative and it's going straight down. So it doesn't have any like trig involved. The 210 pounds is acting up, and it is going to be the sine of 20 now, because this component here is opposite of that arc angle. And then the x component is also, or the x force is also acting up, and that is going to be the cosine of 35 degrees because this component here is touching the arc angle. So those are my two equations. And either one I choose to do, when I solve for x, I should get the magnitude of that unknown force. And essentially, if I solve both of these, I should get the same number. So basically, you'll get x equals some number, pounds, and then you can draw it like this for your direction. But yeah, so that's lesson 7. It's fairly simple. We're probably not going to do a lot of those on the day in class, but they're important to know because they're like the introduction to lesson 8. So lesson 8 goes into rigid body equilibrium. And rigid body equilibrium essentially is no longer at that infinitely small point. So now it's not necessarily a concurrent force system, which means that you might have moments or the body might want to rotate. Equilibrium by definition stays the same, so all the sums of the forces in the moments should equal 0. But now what's going to happen is that because in real life things don't just hover, you're going to have what's called a support, or I like to call them fixtures, but I guess technically they're called supports. So essentially these are the 3 most common, but you can figure out exactly what the support does by thinking about what it causes the body to not be able to do. And basically our next step in this is that we're going to separate the body itself from all of its supports by saying, okay, well, I don't need the support itself in the problem. I need the force that the support is applying to the body. So if you think about it, you can find the supports from, or you can find the reactions at the supports, or the forces that the supports act on the body by thinking about what it can't do. And I'll explain it for the pin support much closer, and then I'll kind of explain it later as we go through them. So a pin support is essentially a hinge. So the body is sitting in this triangle that is pinned in the center, and it can rotate about that hinge this way, right? So that means that the body can't move left or right, which means I can't end up with that body over here. And I know it can't rotate up or down, so I won't end up with the body here, but it can rotate, which means that there's nothing in that pin that is preventing the body itself from rotating. So what does that mean for our pin reactions? So if the body is allowed to move left and right, that means there is no force preventing it. But here, the body can't move left or right, which means that inside this pin, there is some force that is preventing the body from moving left or right. So what I'm going to end up doing is replacing the pin and including F X here, or you could call it, usually that there's like a point that describes where the pin's at, so I'll call it A or something. So I'll call this pin A. So I'll call this A, X. The direction doesn't matter because you don't know it yet. It's one of those things where if you solve for it and get a negative number, you called the direction wrong. And then because this following the same logic, because the support or the body itself can't move up and down, that means there's something inside of this pin preventing it from doing that. So there's going to be a reaction pushing it up or down to compensate for whatever forces in the rest of the system make it want to move up and down. So I'm going to kind of go through that logic again. So this is a roller. So imagine you have essentially something that you're rolling something over, right? This could be like a log going over a like essentially a wheel, so it makes it easier to transport. But what I'm seeing is that this body right here can move that way, right? I can slide it along it. In fact, that's usually the purpose. And if I sit the body right here and push down on this side, it's going to rotate this way, right? So the body can slide left and right, and it can rotate, like about the roller itself. So because of that, these are what are allowed. What's missing? What's missing is that Y component. So essentially every time you see a roller, there's going to be some reaction in the Y direction, because I could push on this part of the roller or the body as much as I want, but the body is being prevented from going up and down because of that roller. So essentially the body's not going to move relative to the ground because that roller is keeping it at a constant height. So a fixed support is kind of like, think of it almost as like a weld. So this bar here is welded to the wall at this point. So if it's welded, can it come off of the wall like up or down? No. So there's a Y reaction. Can it slide left or right on the wall if it's welded to it? No. So there's going to be some F reaction. And if it's welded to the wall, can I rotate it about the wall at all? No. So because it can't rotate either, there's a moment. So basically what you want to think about is, because there are some motions that the body can't do because of the support being there, you want to make sure that you're considering the fact that that can only be the case if the support itself is applying a force equal and opposite to the remainder of the forces acting on the body to prevent the body from moving through that force in that way. So you'll kind of see that in practice problems. I don't know if I'm explaining it 100% right, but once you see what I mean yourself, my explanation will probably make a little bit more sense. So again, what we want to do here is the next step is to draw a free body diagram, which means that we're getting rid of the supports itself and including the forces that support causes the body to feel. So we're replacing it with all of the support reactions, which are what all of these forces are called. So these are all support reactions, right? So basically your free body diagram should have a certain number of things. You need to include the forces that act on the body, whether they're given or whether they're the ones that you found from the reactions. You need to include dimensions, so you need to include any kind of lengths or any angles that the forces might be acting at. And then you need to include the sign convention. So kind of going back up to this one, what does the sign convention mean? The sign convention would mean something like including your positive directions. So that would be something like that. So a drawing like this indicates to whoever's looking at your work that X is positive, Y is positive, and counterclockwise is positive. And that's important when you especially go to write your equations, because then people can see where you might have made mistakes with signs. So the sign conventions is something that a lot of people forget to add, but it is important to do so. The things that you shouldn't include are the supports themselves. So don't put a roller in your free body diagram. Don't put any walls in your free body diagram. Basically, your only thing that you should include is the body itself. And you'll see what I mean when I talk about the body itself when we get into practice problems. So generally the steps that you need to follow to solve for these problems um, is kind of similar to the ones for particle equilibrium, but not exactly the same. So the first step is to read the problem and draw the information that's given to you in the words part of the problem onto the picture that they give you for reference. So this can be messy. This is ideally something that you just want to make sure you're information dumping on. So the problem that's given to you on the worksheet, or I'm sorry, the drawing that's given to you on the worksheet, like the picture that comes with the problem, draw on that, write on it, make sure everything makes total sense to you on that drawing. Then your next step is going to be to clean that drawing up. So make it a free body diagram, which means don't include any of the extra fluff in the problem. So don't include any walls, any supports, anything like that. Don't include any of that. What you want to include is all of the stuff that might be potentially important to you. So the forces that are acting on the body from the problem, the forces that are reacting on the body from the things that you are removing, so any of the supports, any of the dimensions that were given to you in the problem, any angles that you were given in the problem, and you want to identify where all of your unknowns are in that problem. So essentially, your unknown could be a force. Your unknown is commonly pin reactions, or your unknowns are usually reactions of some sort. Um, they could be dimensions. They could be something. They could be any piece of information that you would need to complete the free body diagram. Then from there, once you identify what your unknowns are, you want to write your equations. So the important thing, the most important thing to remember with your equations are these arrows here, because that tells the person again which direction you're calling positive. So you have to include them in your free body diagram with something like that. And then you also have to include them in your equations. So that's important. And then all of your signs in your equations should be based on these arrows. So if something acting in the free body diagram is pointing to the left and I just called right positive, that needs to be negative in my equation. The other thing to remember is that in the force equations, it's just going to be the exact numbers that are acting on the body, right? So it's going to be like the magnitude, and then if it's got an angle associated, it'll include that. But for the moment equation, don't forget that the definition of a moment itself is the force times the perpendicular distance. So don't forget that this is something that you have to consider. And then the next step is to solve for your unknowns. Another important thing to remember is that because you only have 3 equations here at your disposal, you can only have 3 unknowns at the most, which means if you have 4 unknowns, you either forgot to read something in the problem, you forgot to connect some information that was given to you, or there's some relationship that you haven't noticed yet. So other than that, the only other thing that I wanted to talk about is what your answer should look like. So because we're talking about forces and moments in your problem as your unknown, you need a magnitude, so some number with the correct sig figs, that's important. And then you need some units, which will either be, for if it's a force, it'll either be pounds or newtons, or some like scale of those. And if it's a moment, it'll be pound feet or newton meters, or some scale of that. And then you'll need some direction, which is either up, down, left, right, clockwise, or counterclockwise. But then it only makes sense if you have some kind of reference to where that's happening. So, for example, if we're going up to a practice problem that looks like a bar with a pin reaction here and a roller over here, what we want to do is we want to say, okay, well, I have 2 upward forces, so just saying like 6 pounds up doesn't make any sense. But if this is called point A and this is called point B, this reaction will be called AY and this will be called BY. I want my answer to be like 4 pounds up at point A or 3 pounds down at point B. So you have to make sure that you have, especially with these more complicated problems that have multiple points that forces could be acting on, you want to make sure you're identifying what point it is actually acting on with that in your answer. So equilibrium is a little bit complicated because you're combining not only all of the information you've done to this point, but now you have to consider supports and free body diagrams. So it's going to take practice. Um, but if you need help, you know where I am, you know my number, and you know where to find me. So I will see you guys later.